Welcome back to another video. Electronics from concept to production. We're continuing the AC/DC switch mode power supply design. It's been a long day. Went out and got a Christmas tree. So Merry Christmas. Merry Christmas. Okay, so picking it up where we left it off. Yeah. So last episode we finally figured out the compensation network. So we have selected appropriate values for everything. And yeah, that's about it on this part. Now just looking a little bit over the reference schematic, and 1 nanofarad, 12K, 220. So we have a bit of a difference in our compensator and capacitor compensator in comparison. 1.2, and this is also set, like this value is set, so I think the current on the cathode here is 1 milliampere, which was the lowest you could set it as. And then likewise we got this value, I think the same in our design, 825, but it's all based off of what you can choose, right? So it could be that 820 is more common resistor value. Oh yeah, they also have this one here, 1 nanofarad, 500 volt. Optional component, okay. And I was actually looking at this resistor here, between the collector and emitter. This resistor, I think in our design, yeah, there is a resistor there, but it's optional as far as I know. Yeah, it is. I think it is optional maybe, but we should look through the datasheet to see what it says about this resistor. Other than that, it's basically selecting footprint and power rating perhaps. That is the most relevant for this part of the episode. And then we're getting there. We can actually look at what we have so far. Okay, that's it, what we have. But so this is all the main components, but we did some changes. We took away some connectors here too. And now we're adding on a bunch of components. A bunch of, pretty much all of this and this, this. But then we're pretty much finished with the, yeah, okay, so it's the second revision then. So this is actually second revision. But for now, let's just call it first revision, because I didn't really remember to save them. Okay. Yes, let's get started. Let's get started. So in future revisions, I can take this away to just my to-dos. In future revision, we also need to add an EMI filter at the input. That's beneficial, I guess. At least we will do it for the sake of an example, I think, because I really want to just dive down deep into that. Now here I also selected components. Here I didn't. I just selected package. So we can always go over and find every single component. But as long as we have footprint and a 3D model, that's good enough. But it's good practice, I think. Just find an alternative at least. Yeah, but looking quite well, I'd say. Pretty exciting. It'll be cool to actually build this, or to continue with the PCB design, which hopefully if we're doing this effective enough, we can get started on that. Yeah. Having some internet problems, seems. The lag. In the meantime, maybe look into this capacitor here between the grounds. C12. EMI return ground includes Y capacitor C12. There's no explanation about it. But I mean, it's definitely a EMI consideration. Well, but I'm not sure in which direction or if it even matters. But in the case of high frequencies at one side, grounded at the other, I'm not sure. So it's DC coupling at least. Or DC decoupling. They're isolated from each other. In DC at least. And then AC not. Then more of a filter. Well, how do you come up with that? How do you come up with, you know, or resonate yourself to that? Hey, let's check the datasheet. Maybe it's written there. Capacitor. I mean, nope. Nope. Let's see what they call it. CPS. So it's in CPS. Okay. They don't say anything about it. Maybe 1 nanofarad. In case of a normally ceramic feedback, 1 nanofarad, for example, can be put between this pin and ground to smooth the signal. That's what we did. And we should take note of that actually. Just smoothing. Smoothing. So just so we remember. Smooths the signal. Smoothing of the signal. I say more writings or more details than none. So okay, next clamping network. Right. There's no mention of this capacitor CPS. Okay. Note to self is really to, when doing the design, and we're adding these resistors or these capacitors. I mean, I'm taking the notes. I'm taking the notes in a document, but I think it could be good to just annotate in a grid or something and just write down the function. What are they doing? Why are they there? Note to self. Do that next time, or let's do it later. Just to remember, what does this do? Smoothing of the signal. It might be obvious, but at the same time, it might not be. And that would make it easier for us to understand better. I don't know. I feel like too much work at some times, but I think it goes for you to learn more or make more conscious make more conscious decisions where something will work and where you can either decrease or increase certain resistors or capacitors or whatever to make a better design. I think you should do that. Okay. Just look through here quick, see if I see anything. Line or voltage, brownout, line selection. You might return ground includes Y capacitor C12. C12. Damn, I've taken a lot of notes. So this is where we were. We're later simulating LT Spice. I need to structure this better. This is getting in hand. Selecting feedback loop components. Actually, building blocks. Oh. No. Numbered list. I want like chapters and stuff. That could be good. Why didn't I start with that? Come on now. Insert table. Building blocks, smart chips, e-signature, link, drawing, chart. Wait, where was it? Text? No. Tools, insert, each element. Where was I? Where was I? Ah, here. So okay, selecting feedback loop components. So for example, Worst case voltage cross. Compute power, dissipation. And the rating. So B to be less than or equal to 50% of rated power. So if power dissipation is 1 amp, we want at least 2 amp, right? Or no, what am I saying? 1 watt. We need at least 2 watt That's what this is saying, or? No, wait, 1.5. 1.5. Five. Resistors, capacitors, 2 to 3x. Maybe I don't need that. 2 to 3x voltage rating. Voltage margin. Check component, specific limits. Max working voltage of the package. DC bias derating. DC bias derating. Dielectric type. Type, temp, range, and tolerance. Not trying to make it too complicated, but something like that. It's just important for me that I understand. And this is how I would go about doing that, by understanding. Big enough for power and voltage, small enough to keep parasitics low and layout sensible. Okay. Choose package footprint. Sanity check. Where's this function? No, I'm not gonna go too much into that one, maybe. Leave it like as is. But yeah, we check what's the highest voltage that this resistor can see, this resistor, etc., etc. And then we check the worst case current across based off the values that we have calculated. And we compute power dissipation to see how much these resistors dissipate power. And then we add the derating. So where the dissipated power should be less than or equal to 50% of the rated power. So if the component we've selected is rated to, or if the power dissipated in one component is 100 milliwatts, we can select at least 150 milliwatts power rating or rated power. The same for capacitors. So what's the highest voltage? So here we have 2.5 volt, for example. And what do we have here in comparison? Or here? Now we can at least see what's the worst case voltage this capacitor sees, and then we take a 2 to 3 times higher voltage margin than that. So if it's 2.5 here, then maybe a what's the steps? 10 volt, 15 volt? No. 16 volt, 25, something. So 16. We don't need 25, for example, because that would be too high of a margin. We can go with a smaller package. Then we check component specific limits, max working voltage of the package, and capacitor DC bias rating, dielectric type, temp range, tolerance, yada yada. We can get into this too, and we will get into this, but right now we continue. So it would be good if we actually annotated these, and then we can better keep track on what they do. I really want to make like a table or something for them. Start with that. I should really actually do an Excel sheet. Maybe I should do that. That's clean, I think. Let's see if I can make a Excel Google Docs, and I do sheets. Take a blank spreadsheet. This is gonna be the best thing I've done with this, I think. Feedback loop. So in the feedback loop we have, what do we have? We have we should actually, it's tempting to should I rename these specifically, or do numbering, just normal? Can I even call it like div up? You know, like nah, that's really ridiculous actually. Or question mark. What should I do here? What should I do? It's tempting just to have better control over it, but I could also annotate the rest. Yeah, let's do that. I think that's fine. Annotate R18. So we have We start with the components R18. Annotation. So first we have component type, or just component. We do resistor. Annotation. Component, annotation. Value. Worst case voltage, or max voltage maybe. Max current. Function. What's its function? Package. Can you show what I'm doing too now? Something like this. So we can go over and say, for example, here, we have R18, we're looking at the feedback loop. We just want to get like a better So here max voltage is 12. My tea got cold. Max current. So the peak current so I'm not sure if we maybe I do like this in amps, and here is in volt, and here is in insert. I just want to get into a good rhythm, you know, when I'm doing design, that I'm doing calculations for the components that I need. I'm also writing them down so that I remember, and I keep a good track on how I came to the conclusions of 9.5, 2.5 kilo ohm for these two resistors, what the function is, yada yada, worst case voltage, so that I right here, power, dissipation, package, function. Because this, you know, up until these parts I can find out and then calculate this and select appropriate package and stuff. And I keep a track on how I came to that to those conclusions. And I do that to learn this better, right? So okay, enough now. So here is only 2.5 volt. Max current, I think we calculated upper divider resistor for the reference voltage to TL431. And then here, same, just lower. So something like that, just to keep track a little bit. So resistor. Then we have R15. And then we can, of course, R15, R14. R15 is 1.26. And this can also be 12 volts, right? $8.25. Also 12 volt. Function of R15. Yeah, that's right. Because I'm talking to myself in my head. And then we have R16, which is 15K. I kind of like that when you put the values in it, but not obviously not like this or anything. I think it's okay to do like that. But I could also put it here, I guess. Move it a bit up. So it's a bit cleaner. Okay. R1615. And here we can see, I guess worst case this. Or this minus this. C10, 32 picofarad or pico. C11, 132 nano. How the hell do I add? Function maybe? No. Number? Yeah, so these see 12 minus 2.5 volts. $9.5. Calculator. What? Hold on. 9.5. So it's 1 milliamp pad through this. $9.5 squared divided by 1.5. So 9.5 squared divided by 9.5. It's 9.5. Da, 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 da. Yeah, so I guess 1 milliamp pad is through this one, and we have 9.5 milliwatts. So then for package, what's power ratings on resistors? Resistor power rating list. So it's 1/8 watt, 1/4, half watt, 1 watt, 3 watt, 5 watt. Da, 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 da. So cozy, this song. standard resistor values. Standard resistor voltage values. So low power would be 1/8. What could be good would be to wait. I put it up here. Put it up here. Resistor. But I will put another sheet like this. Standard resistor voltage. So we have 0.125. 0.25, 0.5, 1, 2, 5, 10. Which package? Wait, we also have 0.1, which would be 0.63, 0.805, up until 0.805, 1206. Maybe less than 0.1. For CO2. So just a package. Just like if this, or wait, can I compare to a list or something? Compare. Read, compare value to a list and Okay, we're not gonna do that yet, maybe. But at least we have 9.5 milliwatts. Hundred milliwatts, 0. Okay, so we have, what we have to choose from is, so this is all in watt. So this would be 100 milliwatts. This would be 63 milliwatt. So for example, the top one, which only has 1 milliwatt, we could probably get away with 0.0402. So for example, 0.063. But would you go for that low? I don't know. I don't know really. This is 0.1, but which will be 0.63 then. And that applies to this one as well, the same current. Then we would have 2.5 milliwatt also. Let's see, can I word wrap here? Comments. Could I use 0063, but 0402? Kind of want another cup of tea. Tolerance is another thing. So maybe I add column tolerance. %, or 0.5%. Okay, and then it's R15, so we know. Yeah, here we got 12, here we have VKA, which I'm pretty sure I wrote down somewhere what we had. Looking in our notes. 2.75. No, that's wrong. CS pin startup resistor 2.5. V out minus, no. $1.25. Hmm. That was that one. Yeah, the voltage across here, voltage drop across here was 1.25 or something. Okay. But this is definitely why we need to document these things. Diode resistor, we have a voltage drop to the diode and the shunt regulator. So it's 2.5. 2.5 there. Yeah, because it's a regulator, of course. Of course. So we have 12 minus 2.5 again, so it's also 9.5. Yes, over across this one. And then this is 12. Maybe I should start writing it up. 25 volt, 0.5 volt. But the thing is, like, the more you do, the more, harder it is to see. Then again, it's easier to remember, okay, yeah, it's a voltage drop across the diode. Then the shunt regulator, you get this. You don't get that. You get 8.25 across that one. And then a 15. That's another one. Between the reference node and K. Oh yeah. R14 or 15. R14 and 15. Do. 'Can do this squared divided by this. But that will not work. Point 5 squared divided by 1.16. So we have 71. $71.62 milliwatts. $1.5. What if I type? 7.54 milli ampere. So if I take this squared times 1.26, yeah. So here it's more, so at least 50% higher than this one. At least that. So for this, maybe it's better to do that one at least. Then we go up a package size. So 0.15 and 0.805, for example. Because we're cutting it rather close, I would say, if we do 0.1, 100 milliwatts. Then it's like only 25%. Ish. Same here, I guess. Okay, do the same here. .25 is the voltage drop over 8.25 over 825, which gives us a current like so. Or 10 milliampere. So the power is times 825 divided by 82.5 milliwatts. So the same here. Maybe also cutting it close, but I'm not sure how. Nah, I think that's all right. Or so this function sets current there. Da, da. Now this sets LED current, and this sets TL43 cathode bias current. So that it regulates what's happened to the format here. So and provides LED current as well. This one sets the LED current. So it's a function of this one. Sets the output stage 0 at the output stage pole, I think. It's only 10 milliampere through the LED, but also quite little. Then this one, let's see in our documents. This was 10 milliampere. We set maximum forward current through the diode, which is well within the specification. Next, we calculate the other resistor connected between Vout and Vref TL. So that's this one. And here we say feedback min. The cathode min here needs to be milliampere. Damn, I don't have an explanation here then. But this is the smallest feedback current, meaning it has to be less than or equal to this in order to provide enough current, or to at least have 1 milliampere. So between ref and anode. I consider high voltage whatever is required to sync the needed current through the external network. Okay. That is an interesting way to think. So what I've been doing now, and it's not wrong to do it necessarily, but I've been taking the voltage drop in order to, see what current is going through the resistors and therefore which power dissipation they have, and then I select the packages. But in some cases, the actual voltage drop might be unknown and not clear. So for example, at this cathode, it's not 2.5 volt, which I've used it in some calculations, which might be okay in those sense, but here it's approximately 2.5 volt, and the way I understand it is, so here we want it to be 2.5 volt in order for it to regulate okay, wait. It's something like it. So this is some volts above ground, depending on how much current flows through the LED and how much it sinks. So, and how much it sinks depends on the reference voltage. So if it's higher, it sinks more in order for the, I guess, the voltage to be at a certain level that we don't know exactly. So in this case, it's not good to make a wrong assumption on calculations and then we take the voltage drop. So in this case, we take the voltage drop and we calculate it. Here we should assume the worst. Well, why can't I? The full V out, so the 12 volt, and then we calculate. So, because of course it's resistors are cheap, but faults in the field when we have produced a million components of this, that is not cheap. So that's a good way to think about power rating. Don't focus so much on the drop, but what's the highest voltage one of the terminals can see, or what's the highest it could see. So let's say 12 volt over 1.26. Okay, which is 9.5 milli. So instead of 7.5, it's 9.52. Take that squared and multiply it with 1.26. 114. So it's a bit different. 114.28 milliwatt. So then we see that this is actually a little bit like, what if something is wrong and we have higher output than we intended? And then we're close to being that the power rating is not where it should be. So here maybe it's better to do 0.250 then, which would be still the same package with higher capabilities. That's very important to know or to remember. The same, I would almost say the same on this too. So just to assume, because we don't know, so we don't know exactly the voltage drop across this resistor. Is it V out minus the voltage drop of this one, which was approximately 1.25 volt or something. And then whatever this is. So we don't know. So we assume, or we take the worst case. We take the worst case, 12 volt. We'll do that again. 12 volt divided by 0.825, 14.5, 14.5 squared times 0.825, 175 milliwatts. So it's above this again. And it's even higher. More current through here. So is 250 even enough? I say 0.5, but then we go up we go up a size. But this is the design we're doing here. We're doing design where we really know what is going on. Why do we select this package? Well, it's because we have taken into consideration worst case voltage and power tolerances, etc. I like that. Damn, I've been streaming for 1 hour 40 minutes. Time flies. Time flies. Okay. Maybe we look into capacitors. Also. Is it between ref and K voltage small, a few volts? Compensation. Package are here, think about more about noise sensitivity, layout, convenience, handling. So the voltage gross R16. So between here and ref. What about down? So you can't see pole. Current through polystyrene is no real ripple heating. Yeah, at least we can start R18 R18 0.1. Zero 0603 sister. R19 the same. R15. Here we said 0805. The LED, even bigger. 1206. And so then we set all of these except for the compensation network. Okay, wait. So the R comp or 16 sits between VK and VREF. Okay, so it's a few volt basically. Let's say if it's 5 volt cross, which it is not. 5 squared divided by 15 K. It is 16. Right, if I multiply by 1,000, 1.6 milliwatt. So it's okay, wait. Assume 5 volt. Already too high. Do like this. It's already too high, so we have what did I say? Right. 1.6 milli. So even this is too high, but since we're doing this package, might as well do it here too. For robustness. Yeah, 5 divided by 15, 0.33 milliampere. So nothing. Capacitors. So the worst case voltage across these two capacitors. Slightly more depending on your bias things. So, so on this one, assume 10 volts. Conservative. So, don't matter really. Package. So, should be 2 to 3 times the max voltage. So 25 to 50. $25 to $50. Let's say at 25, since it's very conservative. Why not take some? Actually, let's just write 25 to 50. And dielectric. So I add. No. Insert column to the right. Dielectric type. 25 to 50 watts. And then dielectric should be or X7R or C G or C0G. Ba-da-ba-ba. And this is the same as the capacitor, so capacitor voltage. Okay. I'm just curious about the package size here for 25 to 50 volt, and then say dielectric X7R. But at least we made a lot of progress today. A bit about knowingly selecting packages, finding new ways of working, which is very good, I think. Yeah, and then we can eventually, I think we have a package for everything. We can maybe update the PCB, the board design, and then we can check what new components we have. Find where it is in circuit. So C comp 132 nano. I think it's a little bit, I mean, it's dependent on the capacitance. So actually I was supposed to write that here, 0603, 132 nanofarad. So based a bit on capacitance, the voltage that we assume for, so we want at least 25 up to 50 perhaps. So you have to take into account higher voltage rating. So you have small usable capacitance in the small packages. Okay-ish. So for certain capacitance plus voltage, you often have to go for a higher or a larger package. So even 0805 50 volt then would maybe be a better choice. DC bias is negligible, perhaps. Rule of thumb for compensation caps. Use 50 volt X7R 0603 or 0805 if you like bigger, up to 100. Let's go for this 50 volt 0603. And this, I can just leave that there. It doesn't have to be, I don't have to explicitly say what I'm selecting. It's more about package in this case. So 0603, so we do that. So this one, capacitor. C0603. And the same for this one. So, what did we say for this one? R16. Check the spreadsheet. 0.1 watt 0603. Just 0603 there. Just really curious. This is the only one we don't have a selected footprint for. Simply because I didn't have an explanation of how to choose it. So in the reference schematics is 1 nanofarad. 500 volt rating. Oh, I'm getting tired standing. Jump up and down a little bit, maybe. That actually helps. Soon we're done. We're done for today, though. Okay. Yeah, we leave that one for next time. Although it would be nice to select it before we build and everything, because we can perform a ERC, input power pin not driven by any output power pin. What about now? Symbol has been modified in library. Come on now. Okay. So, and this could be left open. I'm pretty sure. Wait. Where's the X thingy? Here. That's the X thingy. Input power pin not driven by any output power pin. So, yeah, we're This is correct, to put power flags here. We're just saying that we have a source for this input. So it's an input power pin, and we say that here we have a source, basically, which is this biased here through this voltage divider. The same with the VCC. It's from the auxiliary winding. I'm pretty sure that's all right. Let's update the PCB. Cannot add C8, no footprint. Oh yeah, that's fine. Damn, check that out. Yes, we have these. We have all of those. Check it out. Catch. Was it not added? Oh yeah. Oh yeah, oh yeah, of course. It was already there. So here we have it. We have more components. We have almost everything. We're missing that one. This resistor. This resistor, this capacitor, this resistor. This one. Cool. Okay. Gonna call it a night. Thank you so much for watching. You have been a terrific audience. Thank you for watching. And until next time. Ciao. Ciao, ciao. Sleep well.